So audio synchronization is an old technique. Many software actually do it for you pretty easily, usually by a single click. So the situation is like this. I have one recording from my desktop capture, C, D, E. So here I say C, D, E, and from my phone, I have a capture of the same audio, but from a different source, so there's gonna be lag. And there's no logic here. There's just a common segment where I say C, D, E, which is common in both, but either of them have extra sounds. So the goal is to synchronize these videos to make sure the CDE part, which is common in both, match each other. So in Adobe Premiere, for instance, you should be able to right click on both clips, click synchronize, choose the audio track as reference here and click sync. It says could not synchronize because the selection match does not exist. Adobe engineers fix this issue. People pay hundreds of dollars annually for your software and it's not even able to do this basic task of audio synchronization. So try at least to implement this Shign algorithm, which I'm about to show, into your software. So what I'm trying to do is using Python, get a trimmed version of one of these audio clips that can synchronize perfectly at the beginning and they will say the same thing. So CDE. CDE. While keeping the rest. F, G. So here I'm gonna use the Librosa library to load the audio file, but as well I'm gonna use this particular algorithm called Shign. This is the GitHub repo, where you can do some basic audio manipulation, but as well you can get the lag or estimate a difference between two audio files. And using the lag, we'll be able to get the offset and sync the audio files. I'm also going to use the two files that are recorded separately. The goal is to get this trimmed version, so let me get rid of it for now. So this is one source. This is my desktop capture, C, D, E. And this is the second source, which I recorded from my mobile phone. That's my face. Okay, let's load the necessary libraries here. So I'm going to import Librosa to load files. You can use a pathlib to manipulate different files in the current working directory. I would like to always display the waveform of audio, so I'm going to import matplotlib as PLT. I've also cloned the repo here for Shign. So Shign is a folder. Inside it, we have a module called Shign. So to access a module in your current working directory, you would say from Shign import, and you can have access to every module inside that directory, which is Shign here. I would like to also listen to the audio as I manipulate it after each step. So I can say from IPython, since we're in Jupyter Notebook, display import audio. And I want to trim the original video file without re-encoding or without loss of quality and without spending hours re-encoding that. So I'm going to import subprocess so I can do the trimming using FFmpeg. Now I have two file names. One of them, let's call it fn1. I'm gonna put it in a path object that I imported. And I just copy paste the name of the file. That's my desktop capture. And I have the second file, again in my current working directory. That's my mobile phone capture. So I have both of them here. And let's load one of them. So let's call the first one audio 1, loaded using Librosa, pass in the file name 1. It's gonna give me the audio and the sampling rate. Let me call it SR1. Let's look at SR1. So Librosa load. So it's gonna give me a backend warning. It says PySound file doesn't exist. I'm working on Windows, so a lot of sound libraries are not supported on Windows. But we get 22,050 sample rate, samples per second basically. I can just copy paste the same chunk of code and call it audio 2 and sample rate 2, open file 2. Okay. We can now take a listen to both of the audio files. So audio, for data, let's pass audio 1. For rate, let's pass SR1. Take a listen. C, D, E. Okay, so we have this here. And the second one, audio 2, SR2. It comes in much later. A, B, C, D. So you can see it's around 7 to 8 second lag between the two. And we should be able to detect that lag or offset between the two audio files. We can have a look at audio 1's shape. and also audio 2 shape before we plot it, because if they are two-dimensional or stereo, we shouldn't be able to plot it. We should turn it into mono. For now, both my microphone and my phone's microphone are capturing audio in mono. We don't need any pre-processing here. So I can now PLT plot audio 1, plot audio 2, make sure they're in the same sampling rate. If not, resample them. You've seen it how to do it before. And let's call PLT legend to get some nice legend that tells us which is which. For legend, I need to pass a label. So let's call the first one label 1, second one label 2. Okay, so these are my two audio files. The blue one is the first track, which started with C right around the beginning, and the common factor is around 55,000 samples. Second track is from my phone, and it starts around 16,000, the orange part, all the way to, let's say, 23,000. That's the common part. Now, since I want my method to work regardless of the size of the audio, if you're doing a podcast, audiobook, a long form recording, you want to take a sample of both tracks. Let's say 10 seconds or 60 seconds of both tracks. You don't want to process the whole 6-10 hours of audio. And you might have like 10 different tracks from 10 different sources. It's going to be really time consuming. So for this method to scale, I'll just take a sample. So that's going to be, let's say, 10 seconds sample from each. After I set my sample size, I can say sample 1 would be take audio 1's first 10 seconds and take audio 2's first 10 seconds. So here, let's say sample size times the sample rate of that audio. That should give you 10-second samples. And just copy paste and change each part for audio 2. Okay, so now I have sample 1's shape, and I can look at sample 2's shape. You see one of them is shorter than the other because I believe the length of audio 1 is only 8 seconds. So a good thing about this way of indexing here is if one of the audios less than 10 seconds, is going to give it as much as it has. You're not going to get an index error in this case. Now, let's try shifting. So the first thing I'm going to do here for shift is to get the amount of shift. So get shift amount. In parentheses, that would be the offset. I'm going to use the Shign library. It has a really handy method called get shift milliseconds, where it takes an audio A, audio B, their sample rate, and it's going to return the amount of milliseconds that audio B, or the second audio, must move to the right to align with audio A. So it's going to give me a number in milliseconds. If it's positive, it means audio B, the orange one, needs to go to the right. If it's negative, it means it should go to the left in order to sync with audio 1. So let me pass in audio 1 as the first argument, audio 2 as the second argument, sample rate 1, sample rate 2, and the amount that it returns, that would be the amount of shift in milliseconds. Shift, let's add milliseconds here just to be safe here. And we get negative 7,870 milliseconds. So around 7 to 8 seconds is the amount of lag between the two audios, the offset, and it's negative, meaning the orange audio needs to go left by 8 seconds to synchronize with audio 1. So that's what we're trying to do. Now, I want to write the logic here and say if the shift amount is positive, so if the amount of shift in milliseconds is positive, it means we need to go right. In other words, we need to cut audio 1. The blue one should be cut because the orange one needs to go right. That's basically the same thing. So cut audio 1 from the beginning. Let me pass that for now. And second case would be shift milliseconds is 0 or positive. Then it is left, or cut audio 2 from the left. So now let's fill these parts. So I want to create a file name for audio 1 since we're cutting audio 1 and the trimmed version. So file name 1 out. Since I put the file names in pathlib objects, I can access a lot of useful functionalities for file name 1. So built in, we have a lot of useful attributes like the stem of the audio file. In this case, it is the name of the file without the suffix. And I can get also the suffix of the audio file, which is the extension, MP4. Same thing with audio file name to img. So whatever audio file I'm trying to trim here, I'm going to add a underscore trim at the end before the extension. So here I would create an f string and say I want file name 1 plus an extension plus the suffix. That would be my modified output file name. And put that into a curly brackets and we're good to go. If not, we're cutting audio 2. Basically here, file name out 2 would be file name out stem and file name 2. Okay. Or we can make it more modular and generic and create just one file name out. And at the end, I'm gonna print the file name out and we can take a listen to it. All right, let me get rid of this pass. So what should we do here? I would need a function, let's say that would cut videos. It should take in, let's say, input video, file name, out video, file name, and the amount of shift or the amount to cut each audio from the video. Basically, in this case, we have around 7 to 8 seconds that we need to cut from one of these video files from the beginning. So I can pass it the offset here. This function should be called in both of these cases. And it's a useful way to find out how to write a function because a priori, if you start writing a function like def cut video, you really don't know what arguments you need to pass here. So the best way is to put it in your code, see what you need this function to do, and then come back and define it here. So here I can say cut video, it takes 3 arguments. Just copy paste them here. And we're basically delegating every task here to FFmpeg. It's a really useful library that supports a lot of functionalities for movie editing in command line. And it also supports trimming audio and video files without re-encoding. Okay, so for my cut audio files, I will need to create an FFmpeg command which can call from subprocess below. So subprocess run, and I can pass in the FFmpeg command. It will take a list of strings and it will stitch them together and run them as if you were using it in the command line. You can also use something like this, like exclamation mark in Jupyter Notebook, FFmpeg, input, blah, blah, blah. We're not going to use this because we want to later be able to copy the whole code in a Python script and be able to get the offset for every file that we get. So starting out, we will call the FFmpeg software. Then we need to pass the input. Input would be the input file name. And you have to make sure here it's not a pathlib object, it's a string because FFmpeg, or more basically subprocess, only supports strings. Then I need to tell it what the starting point is, how much to skip and how much to trim basically. So SS will take you to that specific point, and that point in time is my offset. Offset right now is probably either a float or an integer. We need to make it a string to make sure no errors are given here. And this is the without re-encoding part. Here we pass the codec and ask it to copy. So don't re-encode. It will be much faster and you don't lose any quality. And at the end, the last argument would be the output file name, which should also be a string. I will put comments here where I need to pass strings, not pathlib files, just to remind myself. So this will take the FFmpeg command and run this process. If shift is positive, you need to cut audio 1 from the beginning with the amount shift. So I'm gonna copy this amount shift. This is in milliseconds, and the SS in FFmpeg expects it to be seconds. So here you probably can say divide by 1,000. Okay, so in the documentation, you might want to add input file name, it's a string, output file name, it's a string, offset would be int or float in milliseconds. Just to remind yourself later, or if you put it in GitHub, people would know what the type and the unit of each one would be. What is my input file name 1? That's fn1. Right now it's a pathlib object, so if you print it here, it says the Windows path. It has a useful method here called asPOSIX, which will give you the correct file name as a string. And it is pretty useful because pathlib can work with Windows file names, which are separated using backslash. But the issue is in Python, many other programming languages, backslashes are reserved for things like the new line. So if you print this, let's say you have some other names, it's not going to recognize this as a backslash. It's going to recognize this whole thing as a new line. So here creates a new line and puts the rest of the string there. There are tricks that you can use, like passing R here to interpret this as a raw sort of string. But to make sure it works regardless, you can put it in a passive object. When you want to make it a string, you can call as POSIX. So I'm gonna use this when I call fn1. Output video would be fn underscore out as POSIX and the amount of shift. In the second case, when I need to cut audio to, I would say cut audio to, file name out would be the same variable and the amount of shift as well. So let's run this. It says string does not have the POSIX attribute. Yes, so fn out is already a string. So let me remove it for fn out. Let's get some outputs here. Just make sure the correct part is running. So if millisecond is positive, you would say cut audio 1. So cut audio 1. If it's negative, cut audio 2. So right now, our amount shift is negative. We're cutting audio 2 by around 7 or 8 seconds. So cutting the 7-8 second part on the left. Also, we have to note amount of shift in milliseconds. Right now, if you take this divided by 1,000, you get a negative number. So if you turn it into a string, you get a negative string, and it's gonna throw an error here. So you have to make sure you pass the amount of shift if it's not positive as a negative of that amount. Okay, so let me also get a log of the command I'm running here from the cut video function. This is useful in the beginning for debugging. So this is what we're doing. If the amount is positive, which is not, create an output file name, which is img underscore, oh, I forgot to pass trim here. So underscore trim in both cases. Underscore trim.mov. Then it's gonna call ffmpeg. My second audio, 6263.mov. It's gonna say the start is 7.87 seconds, codec copy, output video file name. Now in this case, I forgot that this output video file name is just a variable, not a string. Okay, after we fix that, we get the img62 trim, and we have the trimmed version right here. Okay, so let's go back into Premiere Pro. Let me get rid of the previous version and let's check. So I have this trimmed version. I can drag and drop it here. Drag and drop into the timeline. And let's see if they are synchronized.
C.
Okay, let's just double check. Let me remove everything, make sure everything's running the same way. So from the beginning, let's listen. Okay, it's not synchronized. What is the issue? Is our algorithm inaccurate? Unlikely. The issue could be arising here because we actually went ahead and said ffmpeg input is this video file, my source file, open it and then seek this specific time. Now my time is a fraction, 7.87, and it might not be the exact time as in terms of frame rate in my input video. So what you need to do is to do accurate seek in an ffmpeg. Accurate seek will go back here, put your seek argument before you open the file. This way ffmpeg will go to this specific time accurately, then open the video. It's also much faster if you have hour-long videos to first seek to that specific part and then open the file from that part. So let's rerun our code one more time. Right now, I need to overwrite the original file, this trim. I either can delete it and run this code, or I can come here and say, by the way, ffmpeg, please overwrite the video without asking me. So Y means I'm answering yes to all your confirmations. Use it at your own peril because it's going to overwrite your files. Okay, so we get another trimmed version. So let's see how good this one is. Let me get rid of the other ones. Drag and drop it here into the timeline. Let's take a listen.
C, D, E.
Yeah, so barely noticeable.
F.
Completely synced up and ready to go. So you can have multiple sources. Doesn't matter. You can have hours long video. It doesn't matter. It can accurately sync multiple source audios or videos. And that's how you do it. Now you can pop it right into a Python script. I created that here. It's pretty simple. I just copy pasted the cut video argument, created a main function, which is later gonna be called if the script is run. So if name equals main, the main function will be run. And what we're doing is taking the input file names from the user, which is parsed using the argument parser. This is one of the most common scripting libraries here. So parser, argument A, video B. You can optionally pass a sample size with the flag S. Default, we use 10 seconds just like before. It's a float. Get the args into the args variable. Pass the input files into fn1 and 2, so just like before. And the rest is just copy pasted from the code that we just saw. So load them, set the sample size, trim, and get a sample for each video file. Get the amount of shift using the Shign library. If the amount is positive, cut the video 1. If it's negative, cut video 2, and go. Let's try out the script. So let me just make sure I have an environment where Librosa is installed. So I can say Python sync audio .py. What's my first input video? It's gonna be, so that's my first, and use my previously first as the second one. So my second would be, and use the sample as the default. Okay, 6263 trim. So we got this right. Let's go back to Premiere Pro and see if the trim version now also works. This is the trim version using the script that we just wrote.
C, D, E.
Okay, so it seems to be working.
C, D.
Yeah, you can mute each channel just to make sure because it sounds too good to be true.
C, D.
Yeah, when you run them together, it seems like there's just one audio source because they're aligned so perfectly.
C, D.
Yeah, you probably need the magnifying glass to notice any lags between the two tracks. In terms of next steps, all we need to think about is optimizing what we did, adding new features to it as well. So one thing I did was to not only get one sample of a relatively long audio file and compute the lag for different sources, but get different subsamples of the whole audio file, compute the lag for different subsamples, and then average the lags together. That's gonna make your estimated lag and also synchronization more robust, especially across time. For this, in my script, I added a new argument called number of samples. By default, it's an integer size 10. And in my code, I said, get the duration of both audio files. In Librosa, you just call get duration. So we have two durations. Take the minimum of the two durations minus the sample size, which by default is 10 seconds. So that's gonna give me the maximum amount of starting point that I can pick. Then I can create an empty list called the list of shifts and go through 10 samples that I have, get a random number between 0 and 1 using the random package, times the max offset. That's gonna give me a value between 0 and the maximum amount of shift, which I calculated here, and that's gonna be my starting point. Then instead of loading both audio files completely, I'm gonna say load it only from that random starting point up to the sample size. So the random starting point could be 10 seconds into the videos, both videos, and it's gonna pick from second 10 all the way to second 20 in both cases. And I'll end up with different samples each time I go through this loop. Then for each different sample, I can calculate the amount of shift in milliseconds, add it back to a list, and at the end, I can calculate the average amount of shift. So that's going to be pretty helpful because we can now calculate the standard deviation of the shifts. We can calculate the spread, plot the histogram, etc. So in one case, I have a longer video. I can calculate the shift pretty easily. I can open the terminal and call in my Python function. First, I'm going to use Anaconda to activate an environment with Librosa. Then I can say Python sync audio. I have two audio files. One of them is called, it's my desktop capture. The length of the videos in both cases are around 37 minutes. Then I'm going to pass the second video as IMG62. In this case, let's get longer sample sizes. So sample size by default is 10 seconds. I'm gonna pass it now as 60 seconds. So take 1 minute, subsamples of the audio, number of samples, let's say 10, just make sure it just runs fast enough. And I can come here and say what the start is. So let's print the start. So let's say starting from start seconds. Or I can even say put them in one line of code. All right. So now it's gonna go open different subsamples. You can later suppress these warnings. They're pretty distracting in this case. Okay, so we're getting the duration. Okay, so it starts from the 508th second almost. And it says the amount of shift is negative 5490. In another run, it says it's negative 5480. So for different subsamples, the estimated shift differs. It keeps starting or seeking different starting points, different subsamples of my original videos, which are 37 minutes long. And the estimated value, even though the difference is really small, you can see each time it gets a different estimate of the offset. So after it runs for 10 iterations, we can look at the range of the predicted offset to see if the range is significant or not. Okay, so the 10 runs have finished. Now we can have a look at the range. Seems like the minimum, or in this case the maximum, is 5480, and the other end of the range is 5530. So there's around 50 millisecond difference in estimation of the offset for synchronization. So 50 milliseconds seems to be a rounding error. It doesn't seem to be significant, but if you feel like these different estimates across time over your video give you different results, you can create another application which will take, let's say, 5-minute samples, calculate the lags for each sample, synchronize 5-minute samples, and create a kind of rolling window, which would be much more accurate. So it depends on your application. How accurate do you want your synchronization to be? At the end, amount of shift, it would be the average of all the predicted shifts. So it's around negative 5502. And the code runs and uses this average amount to create the trimmed version. So this is another modification you can do to optimize your code, make it even better. The downside is it's slower, exactly n times number of sample times, in this case 10 times slower than using one small sample, but it makes it more robust.